Almost 50 years ago, scientists discovered a supermassive black hole at the center of our galaxy.
Neutron stars are remnants of massive stars. They pack incredible density, with just a teaspoon weighing several billion tons. Formed from the cores of massive stars nearing the end of their life cycle, neutron stars represent one of two endpoints for these colossal stellar entities, the other being black holes. Among the universe's densest objects, neutron stars captivate with their mysterious nature. Join us today as we explore the mysteries surrounding these fascinating celestial bodies. According to NASA estimates, the Milky Way galaxy is home to nearly 1 billion neutron stars. Most of the neutron stars discovered to date are youthful, characterized by their rapid rotation that allows their high-energy rays to reach Earth. On the other hand, older neutron stars, potentially billions of years old, rotate at a slower pace and exhibit cooler temperatures, yet they harbor numerous secrets. Neutron stars emerge as remnants of massive stars' cores as they reach the end of their life cycle, following a massive star's explosive demise in a supernova. Its core condenses into a small, ultra-dense mass with a mass nearly equivalent to that of the Sun. These incredibly dense nuclei, known as neutron stars, rank among the most peculiar objects in the universe. Second only to black holes, neutron stars represent some of the densest entities known. Remarkably, a mere teaspoon of neutron star material would weigh over 4 billion tons on Earth. The life cycle of stars, regardless of their size, hinges on a delicate equilibrium between the gravitational pressure pulling inward and the outward pressure generated by photons during nuclear fusion. As stars deplete their hydrogen fuel source for helium conversion, they approach the end of their nuclear fuel life cycle. At this juncture, external energy ceases, and gravity disrupts the equilibrium, triggering the collapse of the star's core. Nonetheless, nuclear fusion persists in the outer shell, causing the outer layers to expand. These expelled outer layers cool down, and if the core retains sufficient mass, it may initiate a new phase of nuclear fusion. In this phase, helium is converted into heavier elements such as carbon. Even stars with a mass ranging from 10 to 20 times that of the Sun reach a level of heavy element production, typically culminating in a core composed of pure iron. However, even this dense element cannot forestall the further collapse of massive cores. In this process, the gravitational force intensifies to the extent that the negatively charged electrons and positively charged protons within the iron nuclei in the stellar core collide, generating a neutral sea of neutrons. The collapse of massive nuclei within a compact body, roughly 1 or 2 times the mass of the Sun, but condensed into a diameter of merely 10 to 20 kilometers, yields remarkable outcomes. For instance, envision compressing the Sun to fit within the confines of New York City, spanning a width of 56 kilometers. However, condensing a mass with a diameter of 1.4 million kilometers into a mere 20-kilometer diameter significantly alters its internal composition. According to NASA estimates, a sugar cube composed of neutron star material on Earth would weigh a staggering billion tons, equivalent to the weight of 3,000 Empire State Buildings, or the entire human race. Neutron stars exhibit such extreme density that their gravitational escape velocity reaches half the speed of light. Consequently, their immense gravity dictates that if an object like a marshmallow were to land on their surface, the impact would generate energy equivalent to 1,000 hydrogen bombs. While marshmallows don't actually rain down on neutron stars, in binary systems, neutron stars can draw gas from their companion stars. When this gas collides with the neutron star's surface at speeds of millions of kilometers per hour, it triggers a spectacular event, characterized by X-ray emissions oscillating thousands of times per second. The appeal of neutron stars extends beyond their density and gravity, boasting various other intriguing features. Neutron stars come in different types, with the most renowned being magnetar pulses or pulsars, often a combination of both. Upon their birth, neutron stars experience rapid spins due to the conservation of angular momentum. This phenomenon can be likened to the spinning motion of an ice skater who accelerates when pulling their arms inward. Similarly, as a star's core diameter decreases during gravitational collapse, the young neutron star spins faster and faster, eventually reaching speeds of up to 60 times per second. As these neutron stars age, their rotation speed typically decreases to around 8 times per second. However, neutron stars that accrete material from a binary partner experience a different scenario. The transferred materials carry angular momentum, leading to an acceleration in the neutron star's rotation speed. Consequently, these neutron stars can be formed with rotation speeds as high as 600 or 700 times per second. Among the 3,000 identified neutron stars, the majority are pulsars, emitting twin beams from their magnetic poles. These poles may not align precisely with the neutron star's rotation axis, causing the beams to sweep across the sky akin to a lighthouse. From Earth, observers witness a pulsating effect as the starlight appears to flicker on and off. PSR J1748244AD, situated in a globular star cluster 28,000 light-years away, holds the record as the fastest pulsar ever discovered, spinning at an astounding 716 cycles per second, or 716 Hertz, surpassing even the speed of a kitchen mixer's blades. Conversely, a magnetic star, or magnetar, is a neutron star characterized by an intense magnetic field. The magnetar's magnetic field exceeds that of ordinary neutron stars by thousands of times, reaching strengths up to 1,000 trillion times that of Earth's magnetic field. This formidable magnetic field can elevate the surface temperature of magnets to over 10 million degrees Celsius. Ultimately, this process culminates in the collision or merger of neutron stars, leading to the formation of a larger neutron star. This explosive phenomenon, known as kilonova or supernova, can transpire in just milliseconds. After billions of years of stellar debris swirling around each other, supernovae release energy equivalent to millions of times that of the Sun, emitting a potent burst of space-bending gravitational waves along with a brief yet intense burst of gamma rays. These stellar detonations facilitate the creation of heavier elements like gold, silver, and platinum. Depending on the size of the neutron stars involved, the outcome of the supernova event may yield a supermassive neutron star that is too massive to remain stable due to neutron decay pressure. Consequently, it swiftly collapses within less than a second, giving rise to a black hole. So, this seems enough for today's video. Please share your thoughts on the existence of dark matter and string theory. We'll be back to you with another amazing video. Until then, goodbye and peace.